Researchers actually have a phrase for it. They call it the grand computational illusion. It's this fascinating phenomenon happening literally every single day, right under our noses. We look at these highly polished interfaces in decentralized finance, right? We see perfectly smooth math moving billions, literally billions of dollars around, and we just trust it completely. But what if I told you that behind the scenes, that pristine, beautiful mathematical theory is hiding a very messy, patched-together technical reality? Welcome back to The Explainer. Today, we are going on a totally wild ride. Seriously, tracking this down was incredibly fast-paced and honestly kind of mind-bending. It all starts with pure, abstract mathematical theory, stuff cooked up by absolute academic visionaries. But it ends with a gritty, super complex compromise right down at the level of physical silicon chips. Today, we're exploring the massive collision between academic ideals and the hard, unforgiving realities of hardware. Okay, let's dive right into this, because instead of walking through our standard roadmap today, I want to hop you directly into what is arguably the greatest expectation versus reality plot twist in modern crypto architecture. We have to ask, what actually happens when developers try to force fluid, infinite math into rigid blockchain networks? Well, the system fundamentally bends. Which brings us to Section 1, the ethereal theory. To understand the compromise, we really have to understand the dream first. The venture firm Paradigm published this absolute marvel of a paper called Orbital, and the developers at OrbSwap engineered it into a stunning mathematical model. And this brilliantly illustrates what they were going for. Look at these curves. Instead of moving along a standard, flat graph, OrbSwap treats the liquidity pool like a circle. They actually designed n-dimensional super ellipses for stablecoin pools using polar coordinates. What does that mean for us? It means converting one token to another isn't some clunky algebraic headache anymore. No, it's treated seamlessly as an angular rotation around a central focal point. It's a seamless geometric dream. Now contrast this with the legacy models we're used to. Legacy models use Cartesian grids. Think of those rigid, jagged X and Y steps from high school geometry. They require heavy division and square root calculations that are notoriously clunky and slow. But polar AMMs? They use smooth trigonometric rotations. In a stablecoin pool where assets are perfectly priced at $1, the perfectly neutral tick sits exactly at a 45-degree angle. This theoretical model totally bypasses the limitations of legacy systems, creating massive capital efficiency and incredibly tight slippage for traders. It's brilliant. But here is where we abruptly hit Section 2, the hard wall of reality. Because look, as beautiful as that theory is, blockchains run on physical servers with incredibly strict rules. And the biggest rule of all? Absolute zero-tolerance determinism. Decentralized networks like the Ethereum Virtual Machine or EVM and Arbitrum Stylus, they require every single node to reach the exact same mathematical conclusion, no exceptions. Because of this, blockchains absolutely hate what researchers call the FPU gambler. That's the floating point unit inside a processor. Sure, the FPU is incredibly fast, but it relies on approximations. It guesses. And if one node's chip chops off a tiny decimal slightly differently than another node's chip, boom, consensus shatters. The ledger splits. Billions of dollars could vanish. So natively, the blockchain outright bans these floating point decimal operations entirely.
To visualize this limitation, think about it like this. Executing the continuous F64 trigonometry from that pristine OrbSwap white paper on a strict integer-based blockchain, it's literally like trying to draw a perfect, smooth circle using only square Minecraft blocks. You can't do it. It's impossible to do perfectly. You are violently forced to chop those fluid, beautiful curves up into discrete, pixelated steps. The theoretical ideal simply does not fit into the rigid box of the execution layer.
This fundamental disconnect brings us straight to Section 3, the PRB math compromise. Now, let's move to see how this builds, because to truly understand this compromise, we have to play digital archaeologist. The official academic papers conveniently leave out exactly how you're supposed to force a 64-bit float into a 256-bit integer blockchain. So, step 1, you read the pristine white paper, and you see clean, beautiful Rust F64 floats calculating sine and cosine. Awesome. But step 2 hits the wall. Arbitrum Stylus' WebAssembly virtual machine actively blocks floating point instructions during contract activation just to protect the network. So, for step 3, you actually have to throw out the PDF and literally dig into the raw GitHub commits of the production code. And when you do, you find that they completely abandoned the academic F64 floats just to survive on-chain. The contrast here is just stark. The academic ideal promised continuous angles and native floating point math. But the production reality? The developers had to lean on heavy scaling libraries like PRB math. To compute sines and cosines, they end up using algorithms like Cordic. And Cordic essentially fakes complex trigonometry using only basic addition and whole numbers. They are effectively simulating decimal math using whole numbers just to keep the mathematical invariant intact. Now, what's really interesting here is this massive scaling factor, 10 to the 18th power. This is called WOD scaling. Because the EVM only supports integers, developers are forced to violently jam decimals into integers by multiplying them by massive factors, just like this one. But here's the catch. Multiplying a sloppy approximation by a giant scaling factor doesn't magically save the math. Actually, scratch that, it makes it worse. It actively compounds those tiny hardware-level errors. It blows microscopic inaccuracies up into highly visible structural flaws.
And that structural flaw leads us right into Section 4, the bloody aftermath.
You absolutely cannot warp pure theoretical math this aggressively without paying a literal price. Just look at this massive spike in execution costs. Arbitrum Stylus is designed from the ground up to be incredibly fast and cheap, right? Basic native integer math costs roughly 1 to 2 gas. But emulating 64-bit floating point math, calculating transcendental functions and trigonometry entirely in software, that absolutely destroys the efficiency of WebAssembly. The costs spike to 12 to 25 gas, or even more, per operation. Every single step of that emulated rotation burns precious, expensive metabolic energy on the network. But gas is really just the start of the problem. The true cost of this emulation is what researchers refer to as informational debt, or the wood chipper effect. By scaling and guessing these trigonometric angles, you introduce permanent rounding errors. The protocol effectively becomes a giant data blender. And especially during times of high volatility, when panic trades are forcing the math across multiple ticks, this severe numerical drift leaves the liquidity pool highly vulnerable. It opens the door wide for arbitrage exploits and sandwich attacks, literally bleeding value directly from the everyday user.
Which brings us to our final takeaway in Section 5, the grand computational illusion.
So the crucial point is this. We have built this incredible ecosystem that promises fluid, perfect mathematics. But underneath that highly polished interface, developers are forced to use wildly expensive, error-prone, integer-scaled workarounds just to make it function on physical hardware. I want to leave you with this final provocative thought. Are we blinding ourselves to the true mechanics of these financial systems by focusing way too much on the pristine academic theory and not nearly enough on the messy, hard-coded reality? Keep exploring, stay curious, and I'll catch you in the next explainer.